Okay. Hello everyone. מתנסים אנשים? יאללה, טוב. Okay. Good afternoon everyone. Welcome to the school seminar. Today we are happy and honored to welcome Dr. Yoav Ben Dor. Dr. Ben Dor holds a bachelor's degree in Earth Sciences.
בוא ניתן לי רגע לשאול את השם. Can we start now?
Okay. So we are honored to welcome today Dr. Yoav Ben Dor. Dr. Ben Dor holds a bachelor's degree in Earth Sciences, a master's degree in Geology, and a PhD in Hydrology and Environmental Sciences, all from the Hebrew University. During his master's studies, he investigated the source of Cambrian age sand in the Eilat region. His doctoral research focused on reconstructing hydroclimatic aspects of late Pleistocene through deep core drilling. Following his PhD, Dr. Ben Dor conducted postdoctoral research studying the composition and age of soils at agricultural revolution sites around Jericho. He then joined the Geological Survey of Israel, where he currently advances the understanding of surface processes using geochemical tools. His work integrates geological and environmental aspects with analytical and computational methods. In addition to his pure geological pursuits, Dr. Ben Dor studies archaeological topics that intersect with geological aspects. In today's lecture, we will hear about his work in characterizing flint sources using the bulk rock geochemistry, a subject that he has been investigating in recent years. Please join me in welcoming Dr. Yoav Ben Dor.
Hi everyone, nice to be here today. Can you hear me well? Okay. Yeah, so they told me before I came here, they told me the people at Haifa are the nicest people to give lectures to, and it's the only place I've been to that you get the applause in advance. So thank you for that. What I'm going to show today is the result of ongoing research. I've been collaborating with many people over the last few years, and hopefully this will grow and we'll have some more collaborations in the future as well. And I'll try to keep it simple enough so we can all understand. If you have any questions at the end, then feel free to ask. So let's just start. So if we think about what is even provenance, we try to do an introduction. So this is a very simple introduction to provenance. Basically, it's a grain of sand or a particle of stone asking his mother where it came from. So this is the main idea when we talk about this word provenance. This is what we mean. If we put it in archaeological perspective, then it would look something like this. Okay, so we find some kind of archaeological artifact, and you will see some examples today. Most of them are from Flint, or in geology, it's called chert. So these are words used to describe the same type of rock. But basically, this is what we're trying to answer. Where did these rocks come from? And if we think about this topic of provenance, then, you know, we always have two perspectives, because we as geologists, we don't care much, at least officially, you know, we care because it's interesting and it's intriguing, but we don't care officially about, you know, archaeological artifacts. So for the archaeologists, it's very clear. You want to know where did the raw material come from? Was it used for different purposes? For example, if I have a certain type of artifacts and other types of artifacts, were they made from different source rock? And then we try to discuss why. For us as geologists, we can think about it as an analog to studying rock fragments over time. So we know, for example, that fluvial systems, you know, they transport bulk rock fragments. And then we can ask, where did they come from and what does it mean? And by doing so, we can reconstruct biogeographical settings and so on. So let's explain what the problem is. Hello. So basically, we want to identify the provenance of a certain artifact or a certain rock fragment that we found. And we can use very different approaches. So one very basic approach could be that we just survey the site, we survey the vicinity of the site, and we say, okay, in the vicinity of this place, I have such and such outcrops. Therefore, it's likely that they brought the raw material from these outcrops. And again, we have an advantage here that we talk about flint, that it doesn't undergo some kind of processing apart from napping. So if we talk about, we later see some examples for iron, for example, it's a totally different process because there they had to smelt it and produce it. Here they just picked the rock from an outcrop and then they converted it into an artifact. So over the years, many approaches were used, and people would say based on color, based on the feel, based on the shape, based on, sometimes you can do a thin section and look for specific fossils or features. And the approach we're going to talk about today deals with the composition. So by composition, we mean the elemental composition of the rock, and we'll shortly see what it means. Now, the main problem, anytime we try to develop some kind of method or conduct some kind of research, that we always have to keep in mind that we have some compromise, okay? We cannot analyze everything all the time. We are always looking for the best way to address the questions that we face. So what we try to do here, and throughout these last few years that we study this question, we try to obviously minimize the workload. So we try to find a method that is as simple as it gets, to minimize also the complexity and the ambiguity, so we can later come up with some useful conclusions. And on the other hand, we try to produce something that is reproducible, reliable, and that can be used more and more. And as we advance, we always keep track of these two approaches. We try to address the specific question, so to publish some results about a specific site, but we always try to also improve the methodology and do it better than we did it last time, okay? So this is the long-term process. So in this presentation, I'm going to show you some steps we've been doing towards developing what we call a robust method. And a robust method should be something that anyone can do, meaning that if I did it in a certain place, you can go to another site and do the same thing and then compare our results, because that's a big problem with literature today. We find many studies that have been done in certain ways and cannot be reproduced. We try to produce an approach that is consistent, that we get the same results, all the time for these specific questions. And we try to develop something that is based on the data. So instead of having something that is based on our premise or what we think we should expect, we try to look at the data and develop from there and build the approach from the data itself. So how do we do it? We sample rock. So we just go to bedrock, and I'll show you some case studies. And we collect samples that we know where they came from. So these samples are called labeled samples because we know where they came from and we know exactly from which geological formation, which outcrop, etc. Then we prepare the sample. We do this by crushing and dissolving. The reason will shortly be revealed. The machines that we work with, they can only analyze liquids. So we have to convert the sample into a liquid form. And we crush an amount that would be representable. Okay, so we don't just shoot a specific laser at a certain spot. We take a few grams and we crush them and we get something that is homogenized and represents the outcrop. Then they are dissolved and then we measure. In the next slide, I will show something about these acronyms. I know it might be a bit scary, but we have these machines that can measure things. Then we look at the data, we refine it, we investigate what it is made of. Currently, this is done in MATLAB and R. And then we proceed into these words that I will shortly explain what they mean. But basically, we try to look at groups inside the data, which is called clustering. And then after we do that, we also try to classify, which means to give it a specific association or specific label. So just to put us all on the same page, I put this one slide here that explains one of the acronyms I've shown earlier. The idea here is very simple. We have a machine. It doesn't look like this. I just put this one because it has a nicer picture. Otherwise, you would just see something that looks like a copy machine. But basically, this machine contains a series of magnets. And these magnets, they can separate the elements that inside the solution So the solution that we feed to the machine, the magnets can separate them, and then they can tell us how much we have of each element. So maybe some of you heard about isotopes and these kind of things. Here we're not talking about isotopes. We're talking about getting the composition of the sample based on the periodic table. So we can get the amount of potassium, the amounts of calcium, the amount of vanadium, etc. And we can measure roughly something like 40 elements, okay? It depends which standards we have, how accurate we want to be, but something like 40 elements, and the machine does it based on a specific relationship between charge and mass, okay? Because each of these atoms, each of these elements has a different mass and a different charge, then the machine can separate them based on magnetic field that it generates. Okay, so after having this introduction and this basic idea of what we're trying to do, let's look at the first case study. So the first case study was published a couple of years ago, and it's based on a survey that was done in the Negev Desert. In the Negev Desert, we try to address these questions. So first, we wanted to ask, can we separate different flint sources? So let's say that we have, in the Negev, we have outcrops of the extraction and reduction sites where people actually went and started napping of flint at site and then took this flint with them. So we try to ask, can we even separate between them? Can we identify different sites, different areas, different formations, etc.? Which features are most important? And can we classify some unlabeled archaeological data? So the last question can be thought of as, if we have a data set that demonstrates the composition of natural sources, can we later on go to an archaeological excavation, take some artifact that we don't know where it came from because it just looks like chert, like flint, and then compare it against the data set, and how do we do it the best we can? Okay, so most of the actual work here, the field work, was done by Meir Finkel and some friends, some colleagues, and he went all across the Negev and he sampled different geological formations. And we have a total of 9 sites. And one of the innovations in the current study, this one, is that instead of taking 1 or 2 samples from each site, it took 10 specimens. So we have 10 specimens for each sample. And this means that we can not only just give some idea of the composition, we can also describe the variance. So we can describe the mean and the variance of the compositional data. So this was a great advancement that was made. And this was made possible because of recent developments in methodology. So we have 9 sites. 9 sites were sampled. I say sites, but actually I mean outcrops. I don't mean archaeological sites. And then we have 10 specimens from each of them. And then in addition to that, we have also artifacts and debitage and stuff like this. So they underwent crushing, homogenization, and then we measure these 39 elements, okay? And they were measured using this machine, which I showed you before, okay? So this machine that uses the magnetic field. Then we moved into analysis of data. So this is how it looks like in terms of the geological section. So we have here Cretaceous flint, which is an episode during which there was a deposition of a lot of carbonate rock in Israel. And these carbonate rocks, they also contain flint nodules. And at the end of the Cretaceous, we have the deposition of a substantial chert formation. It's called mishash. It's what forms these nice waves of brown rock close to the Machteshim area, or when you go down to the Dead Sea. And then later on, we have Eocene chert. And this is a chert that also comes from carbonate strata, for example, as we have in Ramot Menashe, not too far from here. So we have equivalent rocks also in the Negev. And you can see they come from different formations and they can be actually classified by different hierarchies. So they can be classified based on the era, so Mesozoic and Cenozoic, and they can be classified based on the age, so Cretaceous, and they can be classified based on the geological formation and based on the specific outcrop. So we would also like to investigate how well can we tell for each site in which resolution can we determine, if we can separate, if we can even identify the different sources. And in addition to that, we have 17 objects from excavations that were carried out in Feinan. And we wanted to compare these 17 objects against these 90 that we already sampled. So this is how the data looks like, okay? After you send it to measurement, you get something like this. And, you can imagine there's more than one way to analyze this data. And this could be very problematic because if we start to analyze the data in a certain way, we always question if we're doing it in a way that helps us say what we already wanted to say, right? So if we want to claim that there's some difference between this and that, we might look at the specific column, the specific element that gives us the answer we want. So we try to avoid that. Instead of looking at each column, we looked at all of them, okay? And I will show you how we do it. But this is the amount of data you get from this research. So you get more than 3,500 data points. If we plot them, we can see something interesting. We can see that actually most of the concentrations are very close to zero. And the reason is very simple. All this blue stuff is something close to zero. The reason is very simple because this is chert. And chert is made of 95, 99% silica oxide, which we dissolve. So what we have remaining, we have about 1% of the original rock, and this is what we measured. Also, we can see that some of the elements, they have a very different distribution. So they're also non-normally distributed, which has some applications when you deal with statistics. If we kind of scale the data so they have the same level or the same spread, we can start seeing different patterns. And you can imagine that these are like barcodes, right? So we have some samples that are kind of pale blue here, but more dark here. Some samples that are more dark here and more pale here. We start seeing some kind of patterns, and now we want to see if they make sense. So the way to do that, we want to analyze how similar one sample is to the other one. So we want to have some kind of evaluation for each specimen that we analyzed, how similar it is to all the other specimens, okay? So if I take two specimens, how similar are they? The way to do that, which I demonstrate here very simplistically, we can just measure something like distance. So you can imagine if this was just a two-dimensional data set, we only measure two elements, okay? Calcium and potassium, for example, or magnesium and iron, whatever. Then we can measure the distance, right? That's very easy. You take the y coordinate, you take the x coordinate, right? Pythagoras, and you calculate the distance. This can be expanded to any amount of dimensions. So we can calculate what we call the similarity of each specimen to any other specimen. So here, for example, you can see that the distance from specimen 1 to specimen 3 is relatively small. So it's going to get a small value. This is why it's painted blue. Okay, a small value between 1 and 1, which is 0. But between 1 and 3, it's going to be pale blue, okay, because they're similar. On the other hand, the distance between 1 and 2 is quite big. So they're less similar. Because they're less similar, the value is going to be higher. So they get this kind of pink or orange color, and so on. Okay, so we can do this for any pairwise distance. Okay, so this is from the perspective of specimen 1. This is from the perspective of specimen 2. You can see all the distances, and so on until we build all the matrix. Now, if we do this for the 90 specimens we have, we get this matrix. And this matrix might be a bit frightening at the beginning, but actually we can see a very nice pattern in it. We can see that the 10 specimens, for example, that came from this geological formation, whatever its name is, let's call it A, they are pretty similar because they're dark blue. Dark blue means close to 0. On the other hand, when we compare formation A to formation E, which is here, this seems pretty dissimilar. So they're not similar. So when we see this kind of pattern that goes along the diagonal, that's pretty reassuring that we're on the right track. It means that the samples that come from the same outcrop are more similar to each other than they are similar to the rest, okay? So this seems like a promising direction, like a promising lead. And then we can use this matrix and present it in a slightly different way. We can also calculate the averages. So here you can see this is by formation. We can see the average distance between the specimens compared with the average distance to another formation. And again, we can see pretty reassuring pattern. You're not geologists, so I'm gonna skip why I painted these with red rectangles. It's not that important. But then we can take this initial measurement where we constructed the similarity matrix, and we can calculate what we call clusters. So we can start clustering the data based on their similarity. And here you can see that we have two clusters forming by joining specimen 1 with 3, and then another one forming by joining specimen 5 with 4. And then we join these two together, so we get this orange distance between the two clusters and so on. So this is called hierarchical clustering. And once we do it, we get this kind of tree, which is nice to interpret if it works well. And you can see here that specimens 4 and 5 are pretty similar. That's why the height of the branch is pretty small. And specimens 1 and 3 are pretty similar. And these two clusters are also rather similar, but all of these guys are very different from this one. Okay, so we get this kind of idea of how the sample spread. If we do this for the geological data, and again, when we run this calculation, we don't tell the computer which specimen came from which site or which formation. We just tell it, please let us know who are more similar to each other. Then we get this really nice, it's not very important that you read the actual text, but what we can see is that they spread really nicely. So the computer can tell pretty fairly well that each geological outcrop or each geological formation has a unique kind of signature or pattern, and this is also pretty reassuring when we get that. The next thing we can do, we can add the unlabeled samples. So just like we did originally with the geological samples, with the specimens that are labeled, we can now add the unlabeled samples. And these are artifacts that came from an excavation, an archaeological excavation in Flint. And you can see that they have two kind of patterns. First pattern is a pattern that has a blue shade here in the beginning, which is pretty similar to these cherts that came from Mesozoic strata. The other kind of pattern is a pattern that has here the orange colors, and then on the other side it turns blue. So these guys are more similar to flint that came from Eocene strata, okay? So these are like dinosaur carbonates, dinosaur cherts, and these are mammal cherts, okay? So this is after the KT boundary. Now we have some idea that some of these specimens came from this kind of flint, whereas others came from this kind of flint, okay? So we can repeat the same exercise with this as well. And you can think about it like a barcode, okay? So you can see here that this sample has a certain barcode, this sample has another barcode, etc. Then when we calculate again the tree, you can see that we get some kind of pattern. So here we have the artifacts that came from the Neolithic site or the Neolithic strata at Feinan. And here we have the artifacts that came from, I think it's bronze. Yeah, I think it's early bronze Feinan. And the first thing that we can see is that during the early bronze, at least for those artifacts that we tested, they only used a flint that came from a Cenozoic strata, from Eocene strata, whereas during the Neolithic, they used both. Now, this could have certain implications. Why did they use it in a certain way? Why did they choose to make these specific tools during this time interval from this kind of flint? This is up to archaeologists to address. We can't tell if it's because it's better or because it's, political issues and so on. But nevertheless, this is some of the insights that we can get. Okay, so I'll wrap up some conclusions for this phase of the lecture, and then we can proceed to more complicated stuff. So generally, we saw that when you collect geological samples, they tend to be more similar to each other than they are to other chert. That's great. It's a very promising ground to build on. We also see some patterns. It skips it, for example, for some reason. Okay, so we also see some patterns that might be used for classification. We also see that if we sample different outcrops of the same geological formation, they are very similar. So this could mean that we might not be able to identify a specific site. We might be limited in our resolution to a specific formation or age. But still, it seems like there's substantial difference between the Mesozoic chert and the Cenozoic chert. One of the questions could be why. It's a geological question. We need to understand it. And it also seems that there's some good difference between the formations. So we can identify the era from which the flint came from and the formation from which flint came from. We might not be able to identify the specific outcrop, at least not with this approach. And we can use it to identify the provenance of an artifact, and it seems promising. So after we did this preliminary investigation to understand the structure of the data and its usefulness, we move to the next step. Okay, by the way, this can also be applied on other stuff. Here we use the similar approach to study iron ores. So it's not limited just to flint, but in this case, again, these are still material that were not actively changed. So this is before smelting. This is just the ores themselves. Right, so we spoke about this. We saw that we can collect the flint, measure, and split it into groups, which we call clusters. The next step we want to do is we want to do classification. So we don't just want to ask if there's any patterns in similarity. We want to actually know, can you tell me from which site or which era or which formation, whatever, any resolution you're willing to tell us, where did this flint came from? And you can think about it a bit like this. So here we can see, first we see some kind of clustering. You can see it just splits by similarity. And then we can see actual classification. So ideally, we would also like to classify the chert, not just to say that it's similar to something. And this is something we're still developing. Luckily, we have quite a lot of data to build on, and you can read more about some of the recent developments in this paper. But the basic things we need to do before we can do any classification, we need to remove the amount of data. The reason is that we have still a limited amount of specimens. We have just a few specimens from each outcrop. So we don't want to feed any classification model with too much variables compared to the number of specimens. So we want to reduce redundant data. And then we want to build some classification models. And these are now called machine learning or artificial intelligence and all that. When we do this, we have to remember that, we have some complexities. I like this phrase. I always used to put it in my teaching because this guy, what he told us is that there are some things we know that we know. There are some things we know that we don't know. But the thing that we should be actually worried about is the things that we don't know that we don't know, okay? So I put it here just to put it in perspective because we try to come up with conclusions, but we always have to remember that maybe when we come to our conclusions, there's some stuff we didn't realize that we don't know yet, okay? Right, so before we proceed, let's do a very simple exercise. You have here two pictures. And I want you to guess which one is the dog and which one is the cat. And I promise you, one is a dog and the other is a cat. It's not a trick. Okay, so everyone has a guess. Try to guess and place your chips. Okay. Everyone made their bets? Okay. Casino is closing. Right. So who guessed it right? Ah, wow. Who guessed it wrong? Okay. Maybe I need to change the pictures. Maybe it's too easy. I need to change the pictures. Okay, don't worry. Anyways, yeah, so the reason I put that here, which didn't really work with this class, is that sometimes we might look at a certain feature and we think that's the one we need, but in reality, we might be looking at the wrong feature. Now, I'm going to show you this now with geochemical data. So this is just a simple plot that demonstrates the composition of a certain rock based on these elements that are called rare earth elements. And when we do these kind of plots, we calculate, specific features. So we can calculate something called the cerium anomaly and something called the europium anomaly. So if I measure just one sample that is labeled, comes from a certain formation, from a certain outcrop, I might be tempted to say that the flint that comes from this outcrop has these features. It has a positive europium anomaly and a negative cerium anomaly. Now, if I measure another sample, I see something else. I see that the cerium anomaly is still low, still negative, but now the europium anomaly is also negative. This means that if I want to identify this group of rocks, I shouldn't do it based on this feature, right? Because it has some variability. If I pick one rock fragment from the outcrop and I measure it, I get a certain pattern. If I pick another one, I get a different pattern. So I should not be using this feature in order to identify this source. If we do this 10 times, we can get some kind of statistics of how repetitive it is. Okay, so the composition of any potential source is not homogeneous, and single measurements might be misleading. Okay, this again, it goes back to these unknown unknowns that we just talked about. And this is how it looks like when we look at all the groups. And you can see here that some of them have huge variance, some of them have small variance, and so on. Some of them overlap, some of them don't overlap. So it means that if I want to separate this group from this one, this feature is great because this group has small values and this group has high values. But if I want to separate this one from that one, it makes no sense to use this feature because they overlap. So the idea here is to come up with some approach that is data oriented, that we can calculate it per the data we measure and not just fixate on something specific. So we can go through all our measured elements, okay? We can look at all 40 elements and we can come up with some grading system. So when the elements overlap, that's a bad element. We don't want it, or at least it's not useful in this context. It might be very useful in another place, might be very useful in a different country, but it's not useful for this study. This one is great. There's good separation between this group and this group. So we need to evaluate this every time. This is what I mean when I say data-driven. And then we can do some statistic stuff and we can decide which kind of elements we want. Later on, after we do this ranking or grading of the elements, we reduce them by looking at their correlation. So we don't want too many elements that are correlated. This could overfit the models. And eventually we can come up with a list of 5, 6, 10 elements that are best for separating the flints we study. Now this will change every time we change the data, okay? Because it might be that this element is great for this data, but if we measure the same kind of, we repeat the process in the Galilee or in wherever, this might be a different element that shows up here. So we have to run this analysis. That's the advantage of doing this by coding, that we can just run it again and again. Now we want to take this data and we want to feed it into some classification algorithm, okay? So just like when you take a photo of a dog and Google tells you it's a dog, right? It's like feature detection. So we have these samples, we feed it into a model, we can repeat the process. and we can use different models. Okay, these are just names for different models. Now they're very easy to apply. We can use many of them. And then we can get, for each of these models, we can get some results. What do you think that this item, where do you think that this item came from? Did it come from Eocene chert or from Mesozoic chert? And we can see here that the different models, we can build some kind of ensemble by aggregating the models. And you can see that they agree pretty well. We have pretty good agreement, except for this one item, that some of the models think it came from a Mesozoic source, and some of the models think it came from an Eocene source. So this would be now classification. So we can classify the unknown or the unlabeled items. This is something we did in quite recently in the sites of Gesher Bnot Yaakov and Mayan Baruch, where we took hand axes. Again, I'm not an archaeologist, so I don't know exactly what kind of items they were, but eventually we repeated the same process. And again, we used different models, and they all came up with the suggestion that the most likely source for these items was Eocene strata. And this Eocene strata is located a few dozens of kilometers away from the sites. So this means that these guys walked for 20 or 30 kilometers to get the best chert they can, and then brought it back to their sites. Right. There's not much time left, but I want to give you some idea on how we can develop this further. When we do this kind of classification, we are limited because we only have, at least for the Negev case study, we only have 90 samples. So another question, a methodological question we can ask is, how many samples do you need? So when we started this research, and I asked the guys, the archaeologists, I asked them, why did you sample 10 specimens from each outcrop? So you guys are archaeologists. What do you think was the answer? Why not? Right? So it's a good answer. Why not? We don't know. Maybe 10 is enough. Maybe 10 is not enough. It's a good question, a theoretical question to ask. How can we address that? So here we did another exercise where we took the data, and again, each kind of data, it has different hierarchical label. So it has the era label, the formation label, the site label, etc. And then it has these 40 elements. And these elements can be modeled through a process called the parametrization. And we can do this parametrization while maintaining the original relationship between the data. So we can maintain kind of the correlation structure of the data set while we do that. And this is very useful. The reason we need to do all this stuff is that we can now generate fake data. So we can generate synthetic data, something that's more common in earth sciences than in archaeology, at least officially. So we can generate synthetic data that mimics or maintains the structure of the original data. Now, once we have this synthetic data, we can ask very different questions. We can, for example, change the amount of data points I have and see how it affects my clustering, how it affects my classification, etc. We can have some kind of evaluation of the robustness of the data. So we can repeat this. This time we build a model with the parameterized data, and then we want to evaluate it. So now we have labeled data that is fake, it's synthetic, and we want to evaluate it. So we need some kind of metrics because we want to do it many times. We want to do it thousands of times, and we cannot look at each result by ourselves. We want some kind of evaluation. And the way to do it is with what's called a confusion matrix. So you can imagine this is kind of a confusion matrix. We have here a lady that is really pregnant, and the doctor says that she's pregnant. So that's good. Okay, that's a good answer. On the other hand, we might have this guy here, and the doctor says he's not pregnant. So this is also good, right? Okay, it goes like this. But then on the other hand, we can have these two situations where a pregnant lady comes to the doctor and she tells her, you're not pregnant. And there can also be the other way around, when someone who is not pregnant shows up and the doctor tells them they are pregnant. So just as a quick way to evaluate how well our model is doing, we can just calculate a very simple metric, and the metric would be the summary. So we sum these two, and we divide it by the total. So if the model, for example, we feed it with 1,000 samples that we know they came from Mesozoic strata, and for 900 of them, the model says they're here, and for 100 of them, the model says they're here, then we're going to have an accuracy of 0.9. It's going to be 900 out of 1,000. And we have different metrics that reflect different properties of the model. Then we can use the synthetic data and start running the model again, and we can artificially increase n. So instead of sending a student to the field to collect 100 specimens and dissolve them and measure them, we can use the synthetic data to evaluate, at least theoretically, to have some idea how it will improve our algorithm, our classification algorithm. And we can see that for the era, classification by era and by age, if we start from 10, we already have a pretty good understanding of the classification. So our algorithm is about 90% likely to be correct. And if we increase it more and more, the improvement is fairly small. So you can see we minimize the uncertainty, but the improvement itself is rather small. Okay, this is the median, the full line is the median. On the other hand, if we want to be greedy and we want to define a specific outcrop the Flint came from, there we have a problem, because what we see here, that when we try to classify by outcrop, that the model is doing worse. And this means that we are overfitting the model. It means that there are too many groups, and the differences between the groups are not strong enough, are not substantial enough. So the total effectiveness of the model is reduced, even though we increase the number of samples, which doesn't make much sense, but that's the way it works, because this metric is kind of an average of a very big matrix that calculates it. Right, so it's about time to summarize. I hope I convinced you that provenance studies of chert or flint is interesting and useful, especially in archaeological contexts, but also we start seeing some applications in geology as well when we deal with strata that contains rock fragments. I presented, we can say if it's already ready or if it's halfway or something, but some kind of approach towards a robust and systematic way to study these kind of questions. This presentation demonstrated how data-oriented approaches can reveal hidden insights. So for example, we can find elements that make sense to measure, even though we would not think that they will be useful. So just because we can scan all these 40 elements, we can somehow realize that a specific element was very useful, but no one else measured it before because it was not part of the concept. In total, so far, we have more than 200 specimens. So we have about 230 specimens by now that were already sampled, crushed, analyzed, etc. So we are building a data set of flint for Israel. Hopefully, this will become like an atlas that people can use. And whenever you excavate and you find flint, you can compare it. If you use the same methodology, you can compare it against this data set we are developing. It will be part of some kind of a Flint archive, the Israeli Flint archive, hopefully. I showed you that different elements are useful in different contexts. So some elements can be useful to separate certain groups and might be not useful to separate other groups. We can quite surely and quite robustly separate different geological eras. So we can, with a great amount of certainty, we can say that flint came from an Eocene or a Mesozoic strata. We can do this not as good with geological formations and probably not very good with outcrops as well, but we could get some guesses. And obviously, there's much more work to be done. If you are interested in that, these are a few papers that have been published so far. There's a few more in progress. Again, it's a developing work. We're trying to also improve the methodology, but also to apply it over different study sites. And there's much more rocks to climb. And if you found this interesting, this is my contact. These are my contact details, and you can feel free to send me an email. And if this email, which is sometimes blocking, randomly it blocks people, and I don't respond after a while, it's probably because it never reached me. So you can send another one to this address. So having that said, I wish to thank you all, and thank you for coming and listening.
Thank you so much, Yoav, for this insightful lecture. Any questions? Yes.
Like the pairwise comparison which you showed in the graph, I think that one was magnesium and iron.
Yeah, but that was just an example. But you have any specific question on that?
Yeah, I mean, when you analyze this, I mean, when you homogenize and do XRD, XRF, whatever, you get many chemical signatures. How do you then choose? How do you make a pair out of it?
Okay, so we first do the pairwise distance. The pairwise distance works by samples. This means it's like the Pythagoras approach, but it can be expanded. So you can have 39 components inside your Pythagoras distance, and it will just be like a multidimensional variation. I just showed it in 2 dimensions because it's hard for us to think in more than 2 dimensions. So just for simplicity, I just showed it. And after we do that, we can ask, okay, which elements were the most valuable to describe similarity that is meaningful for my context? Because I want to find these elements that separate the groups I'm interested in. So if you are doing some excavation here in the Carmel, maybe certain elements will be very useful to distinguish between Carmel chert and Ramot Menashe chert. But if you're doing the same research in the Negev, maybe it will be 5 different elements that are most useful. The only way for you to determine that is to actually calculate it based on the actual data. So these are 2 steps. The first step was just kind of evaluation using the similarity. The next step we ask, okay, which elements are most meaningful? And this would change. Anytime you change the data, it will change. There's no unique solution to this question. I hope this was okay.
In terms of data, it was like approximated which
In terms of?
the data.
I can't hear you well.
Data.
The data. What you're asking if that's a lot of data? It depends. For computational processes, it's almost meaningless because these programs, they are built to deal with billions of data points. All this machine learning stuff, or all this modeling of separation. But in archaeology, obviously, you can't get to this amount of data. So for most of the programming was in MATLAB for these projects. But in terms of archaeology, you're always limited because you cannot send someone to collect 1,000 specimens and dissolve them. I mean, you can, but I don't know, slavery is gone, so it won't be very easy. At least official slavery. Yeah. So again, this is one of the reasons that we asked, how many specimens would potentially improve this kind of study. Yeah. I don't know, it depends. I guess some people will call it a lot of data, like 3,500 points. Some people would say, if you talk to like data engineers and these guys, they would say it's not enough, like less than 10,000 points, there's no reason to approach them yet. So it depends. Yeah.
I have a question, guys. First of all, thank you very much, Yoav, for this talk in which you managed to open your geological world to archaeologists, which is you did it very slowly and patiently, and we appreciate that. I wanted to ask you, what would be the possible meaning of your ability to differentiate between different geological periods in the Flint? Does this necessarily mean that they're separated also geographically, or can different geological formations be found next to each other, and then you can't make any use of your results? What does it actually mean?
Okay, so again, I'm not an archaeologist, but if you look at a certain site, an archaeological site, then these people, you have different ideas. Maybe they brought flint from Morocco, and maybe they brought it right from across the river. So when you start comparing the flint that you actually find to the outcrops that you have around you, you get the first idea. You can say, okay, it's possible that it came right from here, right from across the river. So they just went 500 meters and they brought it. But sometimes when you have this kind of it produces some kind of forcing. So for example, in the north, we saw that they used Eocene chert. So they don't have where to bring Eocene chert from. They had to walk. When you look at the geological map, it means that they had to walk quite a lot to get it. So it means that they knew, back then, 700,000 years ago, they knew that the right chert for their purposes is found in that place, and they've been walking there for millennia to get this chert, to get this flint. So sometimes, it depends on the context. Sometimes you can get some good ilutzim, like some kind of, you reduce the uncertainty, constraints, yeah, but sometimes you don't. It depends on, you never know what you're going to get. So, yeah.
This phenomenon repeats if people went to this Elkin source.
For example, in those sites in the north.
Was this knowledge shared?
So it depends. So every time we find something slightly different, for example, now we are working on a certain site where it seems like they used both types of chert. They used also Mesozoic chert from the vicinity of the site, but then it's up to the archaeologists, to figure out the story. Did they use, for example, the different sources to produce different artifacts? Maybe they knew that chert from this place can produce great hand axes, but chert from that place can produce, I don't know, some other artifact. So it really depends on what you think. And we're also running some research on later periods where they still use chert. And it seems that they were not just opportunistic. They did not just use what they had at site. They knew they have to go somewhere that's the raw material was of high quality, was suitable for the production of whatever they wanted to do. So they knew enough about geology. Maybe they didn't call it Eocene chert, but they knew they have to go somewhere specific to get this material. And sometimes it works the other way around. So you take chert that's found in an excavation, but you cannot find where it came from because your data set doesn't contain something that is very similar to it. So this may raise different questions. This may raise the opposite question. So I find this flint in an excavation, but where did it come from? Then we need to go and search. These are the unknown unknowns I mentioned. Yeah.
I'm not there.
Yeah. Okay.
Wow. Well, you're not that because you have so much data, you do some kind of prediction.
Yeah.
In what way?
You mean, what do you mean by prediction?
Prediction meaning that if you have so much data about this area, maybe you could predict other things from other places that you didn't research yet.
So I hope I understand what you mean. So first, when you actually look at the flint itself, it's almost impossible to tell where it came from because they look very similar. And Meir Finkel, during his PhD and so on, he did these kind of blind tests. So he would go to the Antiquity Authority and show them different cherts. and they would say, ah, this came from there, this came from that, and they all came from the same place. So doing this by eye is very difficult. I think when we speak about prediction is that, for example, now, let's say that I have data from the Negev, but now someone brings me some artifacts, let's say from here, from Haifa. And I don't have yet the possible sources of the Carmel in my data set. Okay, I only have from the Negev, but I can still compare these artifacts to the Negev and see, for example, from which age, geological age of strata they came from. So I can tell, okay, this is some kind of Cretaceous flint. Now let's open a geological map, see where we have Cretaceous strata. Then we can go and sample these places. So maybe I answered your question, I'm not sure, yeah. Okay.
I have
Okay.
hopefully the first one. You showed that the classification algorithm has lower performance on the specific formation or outcrop resolution. Have you any idea about what features could help you that are not, let's say, elemental composition that might allow you to classify them better in the resolution?
So this is a great question, and the only way to address that would be to measure more features, which we haven't done yet. But I know there are some studies using like spectral properties, and maybe this could kind of maybe this kind of analysis would benefit from such analysis. We personally, we're not there yet. Hopefully we will get there someday, but it's a good idea. And yeah, we will need some more features to resolve that. Yeah.
No, thank you so much. For
Okay.
this, talk.
Thank you. Thank you for having me.
כן, מאוד. אתה רוצה לבוא להניח בצהריים?